Swayam Prabha. Digital India. Educated India.
As a water resources engineer, we are interested in looking at how much runoff is generated so that we can find out how much surface water is available. Sometimes we are interested in how much groundwater is also available, but we will first concentrate on the surface water. So out of the total precipitation, which is the driving force behind the runoff, some part of it is lost if we consider the runoff. Now this loss depends on what point of view we are taking. For example, if we look at it from a surface water point of view, then whatever amount of water infiltrates or evaporates is lost to us. If we look at it from an irrigation engineering point of view, then the infiltration is not a loss. In fact, this is what will drive the soil moisture. So the loss will be defined differently depending on what point of view we are taking. Right now we will start with, from a water resource engineer point of view, what are the losses or what we call abstractions. So if we look at the precipitation, over a certain area where there may be trees, there may be buildings, then out of total precipitation, part of it will be detained on the rooftop or on the tree leaves, part of it will infiltrate, part of it will evaporate. Once it reaches the surface, it will evaporate. So evaporation, then there is infiltration, there is some storage on the tree leaves and the building. Then we may have small depressions where water may be stored. So these are not the streams, but they are small depressions which have to be filled, and then water will move towards the river. So if we consider the runoff, so this part which is runoff, water when it falls on the ground, all of it will not reach the streams as runoff. So whatever is abstracted, we will call that as abstractions. As we have seen, there are various components of the abstractions, and these can be written as interception, which is the amount of water intercepted on the, let us say, buildings or trees. Then we have the depression storage. Small surface depressions which will store some water before it goes for runoff. Then we have evaporation. Transpiration. So evaporation may be from the land surface or from the small depressions, also there will be some evaporation. And transpiration is when the plant roots take water from the soil and then transpire it through their leaves back to the atmosphere. And then we will have infiltration, which is the amount of water which is going below the ground surface. Now out of this infiltration, some part may come back to the surface as runoff. For example, if we have an impermeable layer close to the surface, then part of the infiltration may run over this impermeable layer and contribute to the stream. So, that part will also contribute ultimately to the runoff, but for now we will consider that all the infiltration is an abstraction from the rainfall or the precipitation. Interception and depression storage typically occur in the early part of the rainfall, and therefore they are combinedly called initial loss. Similarly, evaporation and transpiration, they are very similar in nature, and the factors affecting evaporation and transpiration are almost identical. So, we combine them and call it evapotranspiration. Or sometimes it is also called consumptive use. So, evapotranspiration includes both evaporation and transpiration from the plants. Then infiltration we will consider as a loss, as we have discussed that the interflow or subsurface runoff we will for the time being not consider. So, let us look at these mechanism of these processes and see what are the factors which affect them. So, we will look at them one by one. Let us start with the interception. Suppose precipitation occurs over a rooftop. So, this is a building, and on the roof when the precipitation occurs, some amount of water will be stored on the roof before it is carried through the drains down to the ground level. Some small amount will be stored on the rooftop, or it will be intercepted by the rooftop. Similarly, when there is a tree, some amount of precipitation falling on the tree will be detained or intercepted by the leaves, and that will be called interception. Out of this interception, there will be evaporation. Similarly, from the rooftop, there will be some evaporation. From rooftop, water may go through the drain and ultimately reach the ground surface. Similarly, from the tree also, some water may fall down out of the intercepted water. Some water may directly fall down from the tree, or some of it may go over the stems and then again reach the ground level. So, these parts are not really lost, but the part which is evaporated is lost as far as runoff is concerned. Now, for a building, if the rainfall intensity is very small, almost all of it may be intercepted. Similarly, for the trees also, if the intensity is small, the leaves will be able to store all of the precipitation. But when the intensity becomes large, then only there is a limited capacity of the rooftop or the tree leaves to store water, and what we do is write the interception loss equal to some storage initial value which can be stored on the rooftop or the tree leaves and there is some factor K, E and T, where E is the evaporation rate and T is the duration of rainfall. This factor K we will discuss in a little while, but let us first look at the rooftop. When there is some initial storage, the interception storage, now there is an evaporation going on while the rain is occurring. So, depending on what is the rate of evaporation and the duration of rainfall, this additional amount which is evaporated from the rooftop can also be lost due to interception, and for rooftop K will be equal to 1. A flat area, or let us say call it rooftop. But if you have leaves, then the leaves are not horizontal, they have some inclined surface, and the evaporation from this whole area will occur. So, K will represent the ratio of the area of the leaf to the projected area or the horizontal area. I will call it vegetation surface divided by the projected area, which will be the horizontal area. This will be greater than 1. So, from a tree leaf surface, we have some initial storage, then we have this ratio K, and E into T gives us the evaporation loss during the rainfall. So, this gives us the entire interception loss from an structure or vegetation, and this typically is about 10 to 20%, 10 to 20% of the rainfall or precipitation. If we have vegetated area, then it is typically 10 to 20%, but sometimes if you have very dense forests, it may be more than 25%. The interception storage is generally around 0.25 to 1.25 millimeter, and this represents how much depth of water can be stored without it flowing off from the tree or from the rooftop into the drains. Now, the next abstraction which we considered is the depression storage. And as we discussed, there may be small depressions on the surface. So, when the rain occurs, these depressions have to be filled before the water runs off to the stream. The amount stored in the depression is lost through infiltration and evaporation. So, the depression storage will depend on presence of depressions on the surface. So, it will also depend on a lot of other factors, and we can look at some of these factors. The type of soil, because the depression storage, the loss from depression will depend on the infiltration. Therefore, the type of soil which will affect the infiltration rate will decide the loss through depression storage. For example, if you have sandy soil, then you have more loss due to depression storage. Of course, the ground surface is important, because if there are more depressions, then there will be more depression storage. So, type of surface, so more depressions typically would mean more loss. The slope of the catchment is another important parameter. So, if you consider two cases, in one the catchment is very flat, then there are depressions. In the other the catchment is sloping and the depressions. Typically there will be more loss in flat catchments and less in steep catchments, because the water will be flowing faster. There will be more time for infiltration here and less here. The fourth factor which affects the depression storage is the initial soil moisture. So, if you have initial soil moisture high, then there will be less infiltration and therefore less depression loss. So, these factors tell us that the depression storage and similarly the interception also depends on a lot of factors, and it is very difficult to estimate the effect of all these factors individually. So, typically we assign some percentage of the precipitation as the initial loss, which includes both interception or sometimes also called initial abstraction, which includes interception and depression storage. So, generally we say this initial abstraction or IA is some percentage of, let us say, k times the amount of rainfall and this is the initial abstraction IA. K is some fraction which will depend on catchment characteristics and will typically be obtained by observing the conditions. This initial loss varies with time. So, if we say that, let us talk about the interception and see how it varies with time. And with time, when we say with time, the rainfall intensity is also an important parameter. So, the rainfall intensity may be changing with time as it may be idealized like this. Now, if the rainfall intensity is less than the capacity of the interception in that area, then all of it will be intercepted. So, what we can show is with rainfall intensity, suppose we say I here and interception loss here, as typically as a percent of I. So, if initially the rainfall intensity suppose is smaller, then interception loss would be a larger percent of the rainfall, and the general curve which we get is something like this, that when the intensity is small, more percent, in fact it may be typically about 80% of the rainfall can be intercepted and then it is lost through evaporation. But as the intensity increases, the capacity of the structures and the trees is limited to store water. So, interception loss remains almost same. It increases little bit because of the evaporation, as we have seen here. With time it will increase slightly because of evaporation, but more or less we can assume that interception loss is almost constant. So, as a fraction of the intensity of rainfall, it will go on decreasing as the intensity is increased. So, with time, if we say that with time we have initially a small intensity, then it becomes large, then again it becomes small, then we would get interception loss. The interception loss would be limited to the rainfall. It may be equal to the intensity of rain in the beginning if the intensity is smaller than the capacity of the area for interception. Then when we have rainfall which is higher than the capacity of interception, then we may have slight increase because of the evaporation occurring from the surfaces. And then again when the rainfall becomes smaller, then it will increase at a constant rate. So, it may become like this. So, interception loss is not constant with time, it changes with time, but what we typically do is assume that it is some fraction. Overall interception loss is some fraction of the total precipitation, which will depend on the catchment characteristics, and also it will depend on what is the distribution of the rainfall, whether there are more number of storms or whether there are less number of storms. For example, over a certain period we may have a few storms of very high intensity, or over the same period we may have lower intensity storms, but they may be more in number. So, suppose we look at this distribution where there are more intensity of storms, but there are only 3, and here there is half the intensity, but there are 6 of them. So, the total amount of rainfall, total precipitation is same in both these events, but the amount of interception loss as a percentage of total precipitation, if we look at interception loss, will be much more because for each storm event the interception loss will be almost same as initial storage. So, if we look at this equation, there is interception storage which would be fixed. There would be some change with time, but if we say that more or less the interception storage is same, interception loss is almost equal to interception storage, we can say that in this second event the interception loss, total interception loss will be 6 times interception loss for a single storm, while here it will be only 3 times the interception loss for a single storm. So, the interception loss will be much higher if we have more frequent storms for the same amount of precipitation. Now, the other factors, other abstractions which we want to look at are evaporation, and typically we combine the transpiration also with this. And call it evapotranspiration or consumptive use. So, if we look at the evaporation, the process of evaporation is, if there is a water surface, so there is filled with water. Let us look at from a water surface how evaporation occurs. Above the water level there will be air which contains water vapor. So, there are water vapor present in the air, there is water below the surface. So, there will be some vapor pressure in the air as well as on this water surface. Depending on the difference of this vapor pressure, water molecules will go either from the water into the air, which is called evaporation, or from the air into the water, which is called condensation. So, if we can write the process of evaporation as change of liquid to gas below boiling point. Of course, you have one change which is because of boiling when the liquid is converted to gas, but below boiling point change of liquid to gas occurs because of the difference in vapor pressure, and this vapor pressure difference, so we can say that this evaporation rate E will be proportional to vapor pressure in water, vapor pressure in air. And typically the water surface vapor pressure will be higher in order to cause infiltration. So, this gradient of the vapor pressure is what drives the evaporation, and for this we need some energy. So, there are two things which are important for evaporation. One is energy source, and the second is some agency to carry this water away from the water surface, carry the air away from the water surface. So, some carrier to remove saturated air from the surface. The energy source is needed to cause this evaporation, but if we have the evaporation without any mechanism to lead this air away from the water body, then the air here will become saturated, and generally slowly the vapor pressure in the air and water will tend to be equal, because as more water molecules evaporate, the vapor pressure in the air will increase and it may become saturated above this water body. So, there has to be some agency like wind to carry this water away from the water surface, and once the saturated water is carried away from this, there will be unsaturated air or less saturated air replaced here on the top of this water surface, and therefore, it will again create a gradient of vapor pressure causing more evaporation. Otherwise, the evaporation will be limited. Once the air becomes saturated, then the evaporation will be reducing with time. So, this tells us that there will be a number of factors on which the evaporation will depend. So, let us look at these factors. So, evaporation depends on, as we have seen, the foremost factor is the water vapor pressure in air and water surface. So, that we have already discussed, that the difference of the vapor pressure on the water surface and in the air will decide what is the amount of evaporation or the rate of evaporation. Then we should have, since the vapor pressure depends on the temperature and the temperature also denotes the amount of energy present. So, water temperature is another factor which affects the evaporation, vapor pressure we have already seen that E is proportional to, or we can write E equal to some constant into EW minus EA. This vapor pressure is typically represented in millimeter of mercury. Both of these are represented in millimeter of mercury, and E is the evaporation rate, typically in millimeters per hour. The water temperature, generally E is proportional to, or E is increasing as water temperature increases. So, E is directly related to the water temperature. As T increases, E also increases. Then the next factor which we have, as we discussed, that if we have wind speed, so if there is no wind, evaporation will continue for some time and then almost be negligible. But if there is a wind, then we have a continuous process going on. So, evaporation again will increase with increase in wind speed, let us call it W, but it will not keep on increasing, because there is a critical value beyond which the wind speed will not affect evaporation. For example, if you take a water body like this and there is a wind velocity W here, then when the wind velocity becomes sufficient to carry this air away from the water surface at the rate at which, depending on what is the rate of evaporation, when the wind speed is sufficient to carry this air away and cause or maintain the evaporation rate, beyond that speed there will be no change in evaporation rate. Or if we draw a curve, wind speed versus evaporation, if the wind speed is small, the evaporation will be small, because air will become saturated very soon, and it will increase as the wind speed increases, but beyond a critical value evaporation will be more or less constant, because that wind velocity is sufficient to carry air away from the water body. And this wind velocity, critical wind velocity, will depend on the size of the water body. So, if we have a water body which is very long, the critical wind speed would be higher, because then we need a larger velocity to carry all this air away from the water body. So, wind speed is an important parameter, because this is the mechanism which will carry saturated air away from the water surface. The next parameter which will affect evaporation is the atmospheric pressure, and this case we have an inverse relationship. E increases as atmospheric pressure decreases, and this is the effect of due to effect of vapor pressure. The other factors which affect the evaporation: size of water body. As we have seen here, the size affects the critical wind velocity, but the size itself will affect the evaporation, in the sense that if we have a water body which is shallow or a water body which is deep, the mechanism or the process of evaporation will be affected by the depth of the water body. In this case, the solar radiation which is hitting the surface, the heat energy will be absorbed by this body, but in this case the heat energy will be absorbed by the lower layer. So, in summer months when there is high radiation, so in summer the water here at the lower level will get heated or will absorb the radiation, and in winter this radiation will be released to the upper layers to cause evaporation. So, in summer typically this will have high, the shallow body will have high evaporation because the absorption by the lower layers is not there. Here some of the heat energy gets transferred to the lower layers, and therefore, the energy available for evaporation from the upper layers is smaller. But in winter the shallow body will have a lower evaporation. So, as we have seen, evaporation and transpiration are quite similar. So, we combine them in evapotranspiration. But transpiration has a basic major difference compared to evaporation, is that transpiration occurs only during daytime. So, if we look at some vegetation, roots extending into the ground, during its growth it will require water, which is generally taken from the soil moisture. So, there is some moisture present in the soil, the root zone, which can be taken up by the tree, and then it breathes out. If the breathes out means it is transpiring. So, the tree transpires or breathes out the water in terms of vapor, but this process occurs in presence of sunlight. So, this is a daytime process, in night time it does not happen, while evaporation can take place during night also. So, that is a major difference between transpiration and evaporation. Although the rate of evaporation is slow during night, but it is still happening. Naturally, the amount of vegetation present, if there are more trees or less trees, will affect the transpiration. So, transpiration has the factors which affect evaporation. For example, the wind velocity will carry saturated air from above this tree. So, all the factors which affect evaporation will also affect transpiration. In addition, the vegetation density, the nature of vegetation, its stage in growth will be the factors which will affect the transpiration. So, evapotranspiration or the consumptive use is affected by a number of factors, and we have looked at some of these factors. The next process which we look at is the infiltration. And infiltration can be thought of as the movement of water below the ground level. So, it is really passing the surface groundwater, the ground level and going below the ground surface. Now, below the ground surface there is an amount of soil here which is saturated with water, and this saturated water is called ground water. So, this is the water table, and the water below this is known as the ground water. Once this infiltration goes below the ground level, then it may be retained by the soil near the top, or it may percolate deeper and contribute to the groundwater. As far as the ground surface is concerned, there is a maximum rate at which infiltration can occur. So, we can define these two terms as to what is the maximum rate at which infiltration can occur, and then beyond what volume of a storage within the soil it will go deeper and contribute to the water table or the groundwater. So, there are two terms which are commonly used: infiltration capacity and field capacity. Infiltration capacity is the capacity of the soil to transmit or allow infiltration. So, either we can say that this is the maximum rate at which water can be infiltrated, and typically we denote it by Fc, and field capacity. So, Fc is rate, which is typically millimeter per hour, and field capacity is the volume which the soil can hold before allowing it to go deeper. So, this is very simply can be thought of as volume holding capacity of soil. So, if you have a soil present here, and let us say we saturate it with water. So, this is saturated soil, and allow it to drain under gravity. So, if we allow the soil to drain under gravity, after drainage it will again have these soil particles, and there will be some water. It will not be saturated with water. So, there will be some air also, but whatever water is able to hold, that will be called its field capacity. So, once the field capacity is satisfied, then recharge to groundwater will occur. So, we have a rain occurring at intensity I, and this is the ground level. Then we have infiltration occurring at a rate of F, and then we have the groundwater, and there will be some recharge to this. So, we can look at various conditions. For example, if I is less than Fc, that means the rainfall intensity is smaller than the infiltration capacity. So, it means that all the rainfall can be infiltrated, and therefore, F will be equal to I. So, this tells us that the ground, depending on the soil conditions, has a certain capacity to infiltrate water, which is called the infiltration capacity Fc. As long as the rainfall intensity is less than this, the entire rain can infiltrate. But when the rainfall intensity becomes larger than or equal to Fc, then F will be limited to Fc. So, the rate of infiltration will have its maximum value as Fc, and if the rain is more than that, even then it would be limited to Fc. Infiltration rate F which is the actual rate of infiltration, will vary with time. So, initially it will be high, so time versus f, and let us say that the rainfall is more than Fc. Initially the infiltration rate will be high because the soil may be dry, but then when rain occurs, the soil becomes wet and the capacity to infiltrate goes down. The other factor which affects the infiltration capacity or the infiltration rate is that because of raindrop impact, some of the soil surface will become rearranged, and therefore the infiltration capacity might reduce. Also, some of the fine particles can clog the pores on the surface and thereby reducing infiltration rate. So, infiltration rate typically will show a variation like this, where it will start with a high value and will decrease with time. So, some factors we can look at on which the infiltration depends. These can be thought of as soil properties, and soil properties typically mean size of the soil, whether it is loose or tightly packed, and so on. So, we can look at some of these. Generally, sandy soils or the soils with larger grain size will have higher infiltration rate. So, sandy soils will have high infiltration rate, and clay will typically have a lower infiltration rate. Then loose soils typically have high infiltration, and tight soils will have low infiltration. So, size, larger size, high infiltration. Packing, if it is loose, typically we will have high infiltration. Then we have permeability. High permeability would mean high infiltration. And generally, if we have initial condition, let us say initial moisture, if initial moisture is high, then we will have low infiltration. So, if we have high initial moisture, we will have a smaller infiltration, because if the pores are already saturated with water, there will be a smaller capacity to absorb further water. So these are some of the soil properties which affect infiltration. There are some water properties also which affect infiltration. For example, turbidity. If we have high turbidity, then water contains a lot of other material, solid material, and that material may clog the pores and will reduce. So, high turbidity means low F. Then temperature of the water will also affect. Temperature of the water affects the viscosity of water, and viscosity affects the permeability. If temperature is high, it will mean the viscosity is smaller, and therefore water can easily go in the pores. So, it will cause high F. So, turbidity, we have seen high turbidity means a smaller infiltration, higher temperature will mean lower viscosity and therefore higher infiltration. So, these are the soil and water properties which affect infiltration, but in addition to these there are some other or one important parameter is impact of raindrops. So, in addition to the water property and the soil property, impact of raindrops will also cause infiltration to vary. There are really two effects which we can look at. One is displacement of fines. So, the fine particles on the soil surface, they can be displaced by the impact of raindrops and they may clog the larger pores, reducing infiltration. If we have grass, reduces clogging. So, if there are fine particles, they can be displaced by the impact of raindrops and they may clog the pores, but if grass is present on the surface, then it will reduce the clogging because the impact of raindrops will not be able to displace that many fines. So, these are the factors which affect the infiltration, and what we have seen today is the abstractions from the precipitation. So, we say that the runoff generated by a precipitation will depend on how much water we have taken out of the precipitation, allowing the rest to go as runoff. The amount of water which we have taken out of the precipitation, it depends on what use we are considering. For example, if we are looking at it from water sources engineer's point of view, then anything which does not go into runoff will be called an abstraction. For an irrigation engineering point of view, anything which is not going for not infiltrating or recharging groundwater or contributing to soil moisture can be thought of an abstraction. So, if there is some precipitation and there is some runoff and let us say there is some infiltration and evaporation, then from water sources, subsurface engineering point of view, surface engineering point of view, irrigation engineering point of view, all these will classify different things as abstractions. From surface resources, surface water resources point of view, evaporation and infiltration would be abstractions. If we talk about groundwater resources, then runoff would also be an abstraction, but infiltration will not be. Transpiration will be an abstraction. For a irrigation engineering point of view, evaporation and runoff both can be thought of abstraction, and the deep percolation towards the groundwater will also be an abstraction. We have looked at the abstraction from the point of view of surface water resources. So, we have classified abstraction as evaporation, transpiration, which are combined as evapotranspiration. We have looked at the interception storage or the interception loss and the depression storage, which we have combined as initial loss, and then we have looked at infiltration. What are the factors affecting all these processes, what is the mechanism of all these processes, and next we will look at what are the measuring techniques. So, we can measure some of these processes, the amount, so that we have a better idea of how much water will be abstracted, so that we can find out from the total precipitation how much will be the fraction which goes as runoff.